Now the circuit changes, because here we have electrical field, and as soon as we get into the coil, the principles of inductance apply, and we start to build a magnetic field around the device. Now that magnetic field, guys, is of the exact same amplitude and current strength as the electrical field, or the PCM, that just produced that voltage and current to drive that motor or coil. Really important diagnostic consideration, which is why I want you to study inductance. It's becoming more and more part of our life and paradigm in understanding these circuits and how they work. Think about this. If I have 14 volts, okay, driving that fuel pump right now, or that ignition coil, all right, and it's an inductance thing now, and I have 11 amps driving that motor. When this inductive energy builds up and has nowhere to go, this same 14 volts and 11 amps is going to come back and work on this diode. Okay, and that diode is slowly going to break down and fail based on heat damage, because we're not supposed to have 14 volts and 11 amps coming back at this driver. It's supposed to be going through the load and then to ground. Does that make sense? So we have to understand that inductance principle. As soon as you flip that motor on, and as soon as you flip that coil on and collapse the field, that inductive energy builds, and it has to have somewhere to go. If it can't make it through the load to ground, it goes directly back and destroys and tags that driver and takes it out. So guys, here's what you can see when you look for this with a current clamp. Okay, as this bottom statement says, when the switched inductive energy has nowhere to go, it travels back to the source that caused it, causing stress and excess heat on components. Now check this out, okay? This is the dire need for a diode in a coil, injector, or motor control circuit. Here we have a motor that's, in this case, 9-volt motor, okay, on that test board that I showed you. Okay, so this setup was done back here on this setup. These captures were done for this class. Now, check it out. We have yellow is current, red is voltage. Now, I want you to see how well managed the current spikes or the flyback is here on the circuit that has the diode installed on our test board. The one on the right that you're looking at is after I pulled the diode out. Now, I'm going to tell you this. I switched this thing, what was it? 1, 2, 3, 4, 5, 6, 7, 8 times. And the second one I switched 1, 2, 3, 4, 5 times. Now, the diode not only is protecting against this, if you think about this, we're holding current, okay, here down to 0.2 to 0.4 amps of flyback. Here, look at what we've got, a full 11 amps. I'm going to tell you something, guys. I never expected to see this during this test, but just switching this 5 times without the diode, that transistor became so hot that it burned an imprint into my thumb and forefinger when I went to pick it up off the board. 5 seconds, flick, 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 flick on the switch with no diode, and that transistor heated up so bad it physically burned the skin on my fingers. So guys, when you want to know what the physical mechanism is that took out that driver for that fuel pump, or that driver for the injector or the ignition coil, this is it. Okay, and when it's coming via pulse width modulation, man, these pulses right here, if it's out of control, are coming fast and furious, and it does not take a week for that PCM to blow itself up in that condition, right? So when we feel the secondary ignition fail in a coil, that's the time to stop the car and get it fixed, not 2 or 3 weeks later after driving it around on the beltway in traffic. So let's take with the remainder of the time that we have and look at some physical waveforms of systems that we've captured on actual vehicles related to Valvetronic motors and fuel pumps. Now, to introduce three-phase pulse width modulation, and believe me, guys, this is a class all on its own. This webinar, this 1 hour introduction to pulse width and three-phase, is actually a 4-hour class, guys. There is a lot, and I mean a lot of information to go over here to understand this. But I want to give you a good general overview, because remember, we talked about modulation itself, bias circuits. We've talked about covered how to measure it with an oscilloscope, what actually creates the pulse width. Now we get into some real high-tech, kinky kind of stuff here with three-phase pulse width modulation. Now this is something that's being used in a ton of automotive applications, Valvetronic motors, all kinds of motors, okay, coolant motors, coolant pump motors for electric coolant pumps on BMWs and Volkswagens, for example. Valvetronic motors that are actually controlling the valve lift on that BMW engine entirely. Okay, it's motor controlled and it's pulse width modulated controlled. Now, what you're looking at on the screen, guys, is a really neat waveform capture, zoomed out a little bit. Okay, or yeah, zoomed out, right? And you can see here, we've got one in blue current. So I have one phase only. And I'm going to share with you, when you're doing motor control tests, I did this for the class so we could physically show the correlation between the voltage control and the current control on that one single phase. But when we're testing motors, we want our voltage, which is your green, yellow, red here, as well as your current clamp around all three phases. Okay. And then you can diagnose one phase at a time to see which one's out. Okay, but for the purpose of this class, I didn't want to have three phases because that just makes the whole screen just one color and you can't really show anything. So here's our voltage, green, yellow, and red. And here's our current. Okay, now what's interesting is you can see the 120-degree transition. Whoops. The 120-degree transition between phases here. Okay, and I'm going to zoom this in for you so you can see it very clearly. But what's basically happening here is you've got somewhere between 12 and 18 motor windings with the permanent magnet here, north and south. Okay, and then north and south. Okay, so what's happening is as they're pulsed at exactly 120-degree intervals, this is phase one, that one's pulsed, then we're going to pulse phase two. Okay, I'm not going to get this right, but I'll try. 2, and then 3. Okay, and what that does is drag the motor in a concentric circle, around and around and around, just like that. Now, in a single phase pulse width modulated control, you'll have 1 or 2 sets of magnets on the stator of the pump, and then one phase triggering 3 magnets at once to do the same thing, or 2 magnets at once. Now, voltage here, current here. Okay, now, how does that translate? If we zoom in, this is the really neat part here. Now, guys, by the way, this is a fuel pump working with a Continental control. That's 3-phase. Okay, and it's on a Mercedes. We also see this in BMW, VW, Lexus, GM, and on and on and on and on. It's in tons of these cars. Okay, now here's the neat thing. This is our pulse width modulated 3-phase. So each one here is your pulse width modulation. Okay. Whoops, PWM of DC voltage. Now, this DC voltage is actually being driven by what they call an H bridge, okay? And you guys are going to want to look this up because H bridge drives tons of your motors today, including your throttle motor. Okay, so the H bridge is going to be pulsing northbound and southbound current pulses to those magnets. It's doing it with 0 to 14 volt DC power, pulse width modulated. Now here's the neat thing, guys. Take a look at how we're getting AC magnet motor control, induction motor control out of a DC driver here. If you follow me, as soon as I take power off of the phase, so right here, we're cutting the yellow phase. Look at what the magnetic inductive energy is doing in this. Now, remember, yellow is just shut off here. Suddenly, the inductive current and voltage continue to run on that phase. Okay, 2 phases in a 3-phase motor have to be connected at all times in order to keep those magnets pulling in one direction. You're seeing that here. Here we have phase red and yellow on, green off. Okay, our voltage continues to fall. Now watch what this does. As I'm triggering and turning on and off 1 or 2 phases at a time. Whoops. Look at what we have there, okay? What we have there is basically, and not my drawing by any stretch, okay, guys, but what we have here is basically a perfect AC inductive waveform running that motor, okay? Amazing technology. Now, this is the current. Whoops, I got to get my pen back up here. Bear with me for a second. Okay, this is the current running the motor. You'll notice that, if you can guess, my current probe is around the red phase here, okay, because you can see that when the red phase is being pulsed northbound, it's on. When it's being pulsed southbound, this is inductive. And we get AC motor operation out of a DC 12 volt driver. Now, guys, again, there is way too much for me to try to cover here in this class. I wanted to introduce you to this concept, to how it's done, to how it's constructed, to how we look at it on a scope, to the now very common 3-phase voltage controls into cars, and wet your whistle for what will have to become a very steep learning curve for those of us that want to get serious about understanding and diagnosing these systems. Keep your eyes out over the next few months on social media, DiagNation's Facebook page, social media, WorldPAC, and MWACA, WMDA, and all these associations for the 4-hour full 3-phase pulse width modulation class, because that's where we're going to get into the nuts and bolts and how to physically test these systems successfully. What I mean by that is important. We've got to be able to test whether it's the motor, whether it is the drivers, or whether it's the wiring, right? We've got to be able to test all 3. And what I'm going to tell you is, at the end of the 4-hour 3-phase pulse width modulation class, guys, you will know exactly how to analyze this waveform that you see on the screen to get these 3 answers. Is it the motor? Is it the driver? Is it the wiring? Really important to get that diagnostic call right. Okay, now just to finish up, here's your current waveform. Remember, this is 0 amps. So we are getting southbound magnetic, and we're getting northbound magnetic pulses running that motor on a DC driver. H bridge, study it, guys. It's amazing. Look at what pulse width modulation actually does now. This is the final slide we'll get to, and then I'm going to open it up for some discussion, okay, after a couple seconds here. But consider blue as our current, What do you think is happening right here? Here we were on the accelerator, okay, and we had a high pulse width. Here we suddenly dump off the accelerator and we have a reduced pulse, okay, and therefore a reduced current. If we throttle the car up again, we increase the frequency here and we get a higher current amplitude and a higher speed on that motor. Again, we let our foot off slowly. The pump slows down along with the pulse width modulation in this section. And then as we rev that car back up and go to wide open throttle, we're back up at full current. Study this, guys. These fuel pumps, these motors work anywhere between 17 and 40 amps, depending on the application. Really high current, really high tech, really incredible power controls here. Remember, in this case, your signal is your power, so diagnose it accordingly. Now, I mentioned to you that pulse width encoding, this is part of the class we just simply can't get to today, okay? But basically, we're going to use pulse width modulation and pulse amplitude modulation to use a combination of power and signaling to create the motor encoding concept. Study that along with transistors and inductance, and you will be prepared, well prepared for the full 4-hour pulse width modulation and 3-phase class. If you're into servicing hybrids, you're going to want to check out our hybrid class, and you're definitely going to want to check out the full version of this course, 3-phase and pulse width modulation. Okay, here's some deeper diagnostic studies for you to end this session, guys. I want you to take this information when I send you your books and really get your head into this. Tank circuits, like I showed you on the screen. Logic theory, okay, AD conversion and DAC conversion, really important because those are the signals you're looking at in power and sensing circuits with pulse width modulation. Remember to study flyback and the diodes, okay? Load drivers, look them up and read about them. There's all kinds of different controls in automotives that we need to understand when we're looking at that waveform, man. It's not just about running the scope and looking for 12 volts anymore, guys. It's a whole scheme. So we've got to understand it. Look at this one, digital baseband and encoding. Study that a bit, guys. It's amazing. Crank sensors, all kinds of stuff. 4-wheel drive motor encoders, all of it work on this principle. You want to understand why that 4-wheel drive isn't engaging? Sink your head into some of these study subjects and get excited about it, because this is going to bring you to the next level. Then we'll look at some mixed modulation and end with pulse width encoding. Study, guys. This is how we get better. Study. Awesome. Now, guys, I want to thank you so much for your time today. I'm going to go ahead and look at some questions here. I'm just going to read these out loud, okay? Let me just get my pen out here that way. By the way, if you have a microphone and you want to ask a question or make a comment, simply hit the raise hand icon and I'll unmute your mic. But I'm going to read a few of these questions. David Moss says, awesome class, Gary. Thank you very much. Can you just confirm how I get the booklet? Yes, I can. Okay. Hold on one second. Let me get us here, okay? To answer your question, and for everybody that's listening and watching, if you want your booklet, we want to go ahead and have you email me directly, GarySmith@DiagNation.com. So the email address is here, gsmith@DiagNation.com, and I will get you your book this afternoon, okay? And you'll have it. It's going to be a PDF, and it's going to be a webinar version of the 4-hour class, including everything that we've seen today. So thank you very much for that question, and we will get you your books here this afternoon. Swapna says to remember the WMDA Training Day 2021. Save the date. It's February 26th through the 28th. This is going to be an exciting one this year, guys. You know why? Usually we're one day. Now we got 2-3 days to play with. So that's going to be an awesome thing. I'm really looking forward to the training day event this year, COVID or not. We need to get out there and learn and study together and have some fun together, right? Next question, in terms, and this is from Carl Dixon, in terms of inrush current, is the 3-phase motor essentially able to get rid of this with pulse modulation control? The answer is yes, it is, because of its ability to change the frequency of the signal as well as the pulse width modulation. Great question, Carl. Yes, it can tune it down to an extent. The problem is the H-bridge by nature, okay, that's controlling this system is 6 opposite configured diodes, basically in parallel, or 3 parallel circuits, okay, that are toggled 2 phases at a time. So by nature of the design of the H-bridge, it is diode controlled. Some manufacturers, if you look at the schematics, Carl, will actually put external diode control packages on those to protect the diodes inside the H-bridge. Really depends on the speed by which they're switching that motor. Fantastic question, Carl. Thanks for asking. All right. Well, I think that's the last question that I see. Guys, I really hope that you enjoyed this session. I'm really looking forward to doing more with you and seeing you, if possible, good Lord willing, on training day in February next year. So with that said, I'm going to go ahead and end the webinar. Thank you so much for attending WMDA Lunch and Learn Tuesdays. You guys are awesome, and really, I hope and pray you and your families enjoy your Thanksgiving. With that said, this is G. Smith signing off. We're going to go ahead and end the webinar. Have a great Thanksgiving, guys. God bless.